Hey, everybody, we're going to go ahead and get started on 5.3. Here we go. 5.3 is a continuation, exponential and logarithmic. We're going to go ahead today and introduce what an exponential function is, and we're going to compare it to a linear. So let's do that first. So remember, a linear function is one where we have this growth that is added to the function over time. So 500 is our slope. And that slope is every time we add another 500, add another 500, add another 500. So 500 is added to y for every increase in x. An exponential function, it multiplies by a fixed value. So that 1.05 is multiplied. It's the growth factor. So that function is growing way faster than a linear function. Recall that in a linear function, we write it as like y equals mx plus b, and m is the slope. That's what we're adding every time on the table. Well, in exponential functions, you have a base of a and the coefficient of c. So you can see the difference in the types of functions. Like this is what the difference in how they look. Sorry. I'm babysitting right now, so you might hear my nephew in the background and Gracie's Corner on YouTube. But there we have it. So we're just gonna first off identify if it's linear or if it's exponential. A is gonna be linear because there is no exponent, right? It's just a linear function. Versus B, it's exponential. See the X value, it's in the exponent. That's why we call it exponential. Okay. From a table, how do you know if it's linear or exponential? Remember, linear is when we're just adding the same thing every time. Exponential, on the other hand, is when we're multiplying. So right here, it looks like we're adding 1.5 every time. So therefore, this will be a linear function because the y values are increasing by 1.5 through addition. So the data is linear. So every time you're adding in the range, that is going to be a linear function. And so we can write a linear function in the form of y equals mx plus b. So you're going to have to say our slope is 1.5 and our b is that 0. Remember that key piece on here. So it's -3 is what maps to the 0. Okay. So when we put that together, we get f of x equals 1.5x minus 3. The 3 came from the table right here, and the slope is how it's changing. Okay, so where it started and where it's changing. So on this one, it doesn't look like if we were saying, oh, this is plus a -12, that's not constant across the board. So we know that that's not what it is. Instead, we're dividing by 4 or multiplying by 1/4 times 1/4. We're getting smaller by a factor of 1/4 every time. So there we have it. For each increase, we're decreasing by multiplying by 1/4. So the data is exponential. So we're going to talk about that being that c a to the x power. C is your y-intercept. That's going to be your starting value. So that's the 16. And then the growth factor is 1/4. So it's in this way, it's actually decreasing. So it's called a decreasing factor. So we have 16 times 1/4 to the x. And you want to leave it like that. Okay. You don't have to multiply 16 and 1/4. The 1/4 is raised to the x power. Okay. So again, when we look at the difference between linear and exponential, we see these two different things happening. One is growing faster, and that's why you have that curvature. So about 4, we're already at 16, whereas in a linear function, at 4, it looks like we're still at 8. So you can see a +2 change on here on the linear side versus a multiplication of 2, a growth factor of 2 on the exponential side. Example 3, find C and A so that the conditions can be solved. Well, the initial value is what maps to the 0. So that's our C value. C is 4. And then how do you get from 0 to 1? It's 4 to 8. So that's times 2. So A is equal to 2. So it should be 4, 2 to the x. Uh-oh. So when we put that together, we get 4 times 2 to the x. Okay. All right, and then we can do it from a word problem as well. Find C and A. So there were initially, that's the beginning, that's the 0 at the start. There are initially 600 bacteria and the number doubles every hour. So our C is 600. And we're doubling every hour. So times 2 is our A value. So we have a C of 600 and an A value of 2. So we put that together, 600 times 2 to the x. Pretty self-explanatory and straightforward. 50 bacteria in the beginning, decreasing by half. So we have a C value of 50, an A value of 1/2. 50 times 1/2 to the x. Part D, 2000 is our C. Now, increasing factor, it increases by 25%. Percentages are different. It's 25% is still 1/4, right? But it's an increase. So it's gonna be 1.25. So the change is 1.25. Anytime you see a percentage that's increasing, it's gonna be 1 point that percent, okay? So our A value is 1.25. So when we write this out, we have 2000 times 1.25 to the x. All right, E. 300 is our C value. And this says decreasing by 20%. So that 100 that we had is now decreased by 20%. So we get 80. So our value is 0.08. Whereas the last one was 100% increased by 25%. So that's why we got our 125. And to make it a decimal, you move over twice. So that's why we got 1.25 on the last one. And we have 0.80 on this one. So we have C, A to the x. Our C value is 300. Our A value is 0.8 because it's a decrease of 20%. All right, so now how does the graph of an exponential function look? Y'all know like the A value of a quadratic tells you whether it's up or down, fat or skinny, narrow or skinny rather. Well, an A value in the exponential functions, if the A value is bigger than 1, then that is increasing. If it's less than 1 or well, between 0 and 1, it's decreasing, okay? So it's called exponential growth if it's greater than 1, exponential decay if it's less than 1. And we saw that a couple times already. So when it was increasing by 25%, that's why it was 1.25. And when it was decreasing by 20%, that's why it was 0.80. So decreasing is when it's decaying. And 1 point something or 1 over 1 rather, is when it's growing. Ooh, my pen is not working. That's crazy. All right. All right, so that's what we have, growth and decay. All right, so you can see your growth factor, your decay factor. So when A is greater than 1, it's growing. When A is between 0 and 1, it's decaying. And basically F is continuous, F is 1-to-1, and there is an inverse for an exponential function, which we're going to talk about very soon. Okay. All right, so let's look at example 4. Use the graph to determine the values for C and A. So we've seen it on a through an equation and a word problem, but how can you find it from a graph? So at 0, where's your function? Right here at 3. So that is your C value. A says how do I get from this to the next value? You know what I'm saying? So like, what is my growth or decay factor? So again, C is 3 because it's a y-intercept. So then we'll use 3 and this point on the graph right here to find our A. And so we have the function of f of x equals c times a to the x. Well, that's 3. And our y value in our point is 6. We don't know a, but we know our x value is -1/2. So you put this all in the calculator and solve for a. Okay. So that's what this says. How can we find a? Well, we have a point, we have 2 points. Anytime you have 2 points, you can find the missing variable. So we're dividing by 3 and we get a to the -1/2 is 2. So what raised to the -1/2 is 2? The opposite of -1/2, how you get rid of that rather, is you square it, but a negative square. That's because -1/2 times -2 makes +1. And that way we'll just have a to the first power. And so 2 to the -2, you can put that in your calculator and you'll see that that's 1/4. So how do you put that in the calculator? Let's stop sharing real quick and see if I can share my calculator. Okay, so here we have, I'm gonna clear this out. So it was 2 raised to the -2. And there you have it, the answer is 4. So we can write it together as 3 times 1/4 to the x. Okay, so now we're at the point where we're doing application problems. Like, when will we ever use this? How is this actually realized in real life? And money is the answer. Compound interest, anytime you save money, borrow money, spend money, there's usually some type of interest formula that's associated with it. So if a principal of P dollars is deposited, principal means the amount at the beginning, the initial amount, with an annual interest rate of R. So that's how much they're charging you. You have to write it as a decimal point though. Compounded or like paid certain amount of times a year, N. Then after certain many years, T, then we'll have A, the amount of dollars in the bank, okay? So for example, suppose you had $1,000. That's the P, that's how much you put in. Deposited for 20, by a 20-year-old worker in a IRA account. So we don't care that he's 20 years old, that's extra information. But it pays an annual interest rate of 12%. So that's R equals 0.12. Okay. It says, describe the effect on the balance. So how much will he actually have? Like, will it go up a lot? How much will it go up by? After 45 years at the age of 65. So again, we don't care that he's 65. All we care is that 45 years have passed. So time is 45 years. If we compound quarterly, this means 4 times every year. So N is 4. That's how many times per year. Quarterly means 4. Okay. So we start off with that information, 1,000, 0.12, 4, and 45. Just getting that information from the word problem is going to be really important. Then you put it into the formula and that's it. Okay. So we're going to have 1,000 for our P. Times 1 plus the rate over how many times a year? I thought it was 4 times a year. This is sorry. It says describe it quarterly versus annually. So we have to do both. So we're looking at N equals 1 and N equals 4. So we're going to compare. And then N times T for this one is just annually. So 1 times 45. and we'll get about $163,987.60 if it's compounded just one time a year. Versus if it's compounded quarterly, we're gonna plug in 4 for that N. So the difference is N is 4 in this one. Okay, because we're comparing them. Okay, so this one we're about $204,503.36. So because the high interest rate for such a long period of time, it results in an increase of $40,000 if he compounded it 4 times a year versus 1 time a year. So the type of question is like, can you compare what would happen if you have different compounding options? Compounding is done more frequently sometimes, and that's called the natural exponent. Okay, so sometimes we don't even say compounded 5 times, 4 times, 3 times. It's like compounded continuously. Every second, every millisecond is being compounded. So that's called compounded continuously. And there's actually a number that represents this, kind of like pi in math. There's another number, it's irrational, it's called E. And that's what E is equal to, 2.71, blah, 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 blah. It's called Euler's number. And that E is actually a letter, but it's also a number, okay? That function is actually just f of x equals e to the x. That's called a natural exponential function. And that's for when something is compounded like continuously without a boundary. So instead of having n be replaced by the value of e, we have a whole different equation. It's for compounded continuously, it's a equals p to the e r t, like that. So we just need to know the principal, the rate, and the time. We don't really concern ourselves with n because n is continuous. And so that's why we have the e in the formula. So 100,000, the interest rate at 12%, 0.12. How much will it be after 45 years? So annually was 163,000. 4 times a year was 204,000. I'm pretty sure this is going to be way larger because it's compounded all the time. So substituting those values into the calculator, 221,000. So it's substantially larger, about 20,000 more. Well, 16,000 more than compounded quarterly. Okay. Next example is just kind of doing the same thing, but like reading through and writing our exponential function and using it to solve. So a number of people who are 100 years old or older are called centenarians. This number in India is projected to increase by 4% each year after 2010 to 2100. If there were 50,000 centenarians in India in 2010, write the function that gives the number after 2010. So the initial value was 50,000 and it's increasing by 4%. So A is equal to 1.04 because there's an increase. So we know it's gonna be 1 point something, an increase of 4%, okay? So our equation is gonna be y equals 50,000 times 1.04 to the x. It says estimate the projected number in 2050. So that's 40 years later. Okay? Because we started in 2010 and we're going to 2050. So you just plug in 40 for x. And we get about 240,000. Let me show you how to look at this from the calculator. Okay, from the calculator, we can say 50,000 times 1.04 to the 40. And that's how we get 240,000. All right, last example. If the quantity initially equals C units has a half-life of K, then the amount remaining after T time in years is given by this equation. So radioactive carbon-14, which is found in all living things like you and me, has a half-life of about 5,700 years and can be used to date fossils. What percent of carbon-14 will a fossil have contained if it was approximately 24,500 years old? So the half-life is K, and we know that that's 5,700. And then the time is given to us in years. So let's write this out. An organism with 100%, like C equals 1 would be the initial amount. So C would equal 1. And then, of course, it goes down, it decays by half every 5,700 years. This fossil is 24,500 years old, so that's T. So we just substitute our values in. Okay, 1 for C. T is 24,500. K is 5,700 because K is your half-life. And then we just substitute that in the calculator. And we find out it is about 0.5. So that's 5%. 5% amount of carbon left in that organism. Okay. All right, that's it, y'all. Thanks for watching.